Thank you. Hi, everyone. I'm Arpita. I'm a Circus postdoctoral fellow at Harvard University. I'm working with Professor Milind Thambi primarily. And I completed my PhD from Indian Institute of Science under the supervision of Professor Siddharth Burman and Professor Narahari Aditi. So today I'll be talking about two-sided fairness guarantees. So before I get into that, here's a big picture of my research areas. My work lies in the area called algorithmic decision making for social impact, where I design and develop algorithmic solutions aiming towards fairness, resource limitation, robustness, and sustainability. My current research involves sequential decision making under limited resources. In particular, I have been collaborating with several nonprofits to provide decision support for maternal and neonatal healthcare programs. These collaborations have led to investigating various fundamental questions which I've been exploring at Harvard. For today's talk, I'll just be focusing on two-sided fairness guarantees. So I'll talk about fairness concerns arising in two contexts. The first one being product recommendations, where there are customers on one side and producers on the other side. And the goal is to match producers to customers in a way which is fair to both of them. The second part of my talk would consider college admission scenario, where there are students on one side and colleges on the other side. And the problem is to guarantee some kind of fairness across everyone. So now first I'll talk about this particular work, which is joint work with Gaurav Patro, Nilay Ganguly, Krishna Gumadi, and Abhigyan Chakraborty. And this is titled Towards Fair Recommendation in Two-Sided Platforms. So what is a recommendation system? In a very general way, recommendation systems are algorithms that are aimed at suggesting relevant items to users. Items being movies to watch, news articles to read, products to buy, etc. Nowadays, recommendation systems are unavoidable in our daily online journeys, mainly because of the rise of online platforms such as Amazon, Netflix, Airbnb, and food delivery apps. Now, an efficient recommendation system is the most critical component of several e-commerce and online advertisement platforms. Let us look at a scenario to understand the recommendation process. Say there's a user who uses an online music app and expects a personalized list of songs or music whenever they open the app. Now, to create this personalized playlist for the user, the online music service would run a recommendation algorithm. Now, this task typically requires learning the relevant scoring functions by using information such as whether the user liked a particular kind of music or disliked it. And then there are many algorithms for learning such relevant scores, like content-based recommendation algorithms, collaborative recommender systems, and hybrid approaches. And once the relevant scores are predicted, the standard practice across several recommendation systems is to recommend the top key relevant items to the users. Because traditionally, the goal of a personalized recommendation has been to recommend products that would be most relevant to the customer. Now, while this top key approach maximizes the satisfaction of all individual customers, it may not be the best post-processing technique when it comes to e-commerce platforms, where they have to balance between producer satisfaction as well as consumer satisfaction. So basically, there are multiple stakeholders in this kind of e-commerce platforms. There are producers of goods and services, for example, restaurants on Yelp, hosts on Airbnb, and also there are customers who consume them. And then there's a platform which sits at the center of the ecosystem, essentially controlling the information access through the recommendation services. So imagine if there's a new song or artist who would join the platform may not be in the top K list of any of the users, and they would never be recommended. Now, to tackle that issue, we consider two-sided fairness for recommendation protocols, where there is a set of N customers on one side and M producers on the other side. And we would assume that these are two fixed sets and it's known. On the customer side, we will imagine that each of them have a limited screen size. Say there can be only 3 slots where 3 producers' advertisements can be shown. And the problem is to kind of select which K top producers to show whenever a customer opens their main screen. And additionally, we will imagine that there is some way to compute the value of a user for a particular producer, and this value is same as the relevance scores for the user. And then because of this K slots, there is an overall constraint that each customer can only be allocated, for example, 3 advertisements or producers. And then also there's a category-wise cardinality constraint, basically saying that category is a producer, and then for a particular user, one producer can be shown only once. So all these 3 advertisements should have 3 different producers. Okay, now on the producer end, a producer gets a value of 1 each time it is shown to any user. So it is kind of indifferent between which user are seeing their ads, but we will imagine for this problem that there is a value of 1 which is additively accumulated whenever a producer is shown to any customer. Now, given that if we have to compute the maximin value of a particular producer, what we would do is we will look at all the number of slots available, which in this case is N multiplied by K, divided by the total number of producers, which gives us 2 for this toy example. And here, every producer would be said to satisfy maximin fairness if they get an allocation, they get shown to at least 2 users. And we will also use this terminology, which is approximately fair maximin share or alpha MMS, where we would say that so alpha is a value less than 1, and we would say that it is fair, or it is alpha fair if the total number of users which a producer is shown to is greater than or equal to 2 multiplied by alpha. So this is a relaxed fairness constraint. Now, if we have to guarantee this kind of a threshold fairness to every producer, then we may not be able to give the top K relevant items to each customer. In that case, we also need some kind of fairness to make sure that the customers, if they compare their recommendations with their friends, they are kind of, they feel it's fair to them. So to define that, we will stick to the definition called envy-free up to 1 good. Now, what do we mean by envy-freeness up to 1 good? Now, this is a well-studied fairness notion in the fair allocation literature, where there is only one-sided allocation. So the agents have preferences for goods, and then the idea is to partition the entire set of goods into N partitions, where N is the total number of agents. Now, an allocation is said to be envy-free up to 1 good if for every pair of agents, see I and J, there exists a good in agent J's bundle, which when you hypothetically remove, agent I do not envy agent J anymore. And I'll describe this with an example where agent 1 values A2 bundle more than A1. So it is not envy-free. However, this allocation is EF1 because when the blue ball is removed from agent 2's bundle, then agent 1 does not envy agent 2 anymore. Thus, this particular valuation is called envy-free up to 1 good. So we will stick to this notion of fairness on the customer side. Okay, so now let us look at some of the related work in the space of this two-sided fairness. So one such results show that if we assume symmetric preferences, which basically means that the utility or a value obtained after a matching for a user is same as that for the producer. So both customer and producer have the same value when they are matched. So this is called symmetric preferences. So if we assume that, plus if we assume binary preferences, that is when either they like to be matched or they don't want to be matched. So if we just have binary preferences with symmetric nature, and also if the values are additive, then EF1 exists on both sides, even when we have dynamically changing valuation. So this particular paper talks about accumulating EF1 over time, and it shows that EF1 should exist on both sides. There's another work which is more close to what we are saying is that if there are if you don't have to assume like symmetricity and only assume additive nature of the valuations, then EF1 exists on both sides under ordinal identical preferences. So identical preferences is when each side has the same ranking over the other side. So these are identical for everybody on the same side. And if the preferences are ordinal, so we don't have values, but we just have a ranking given, then EF1 can be defined according to ordinal preferences, and it can be shown that EF1 exists on both sides. So this is a known result. And also it has been there has been a lot of impossibility results in this space, basically saying that EF1 on both sides may not exist, even if we assume that one side has identical preferences and other side, sorry, this is a typo, other side has cardinal preferences. So then EF1 may not exist. Also, a 0.89 maximin matching on both sides may not exist, even when there are identical but cardinal preferences. And another impossibility result says that if you have to satisfy EF1 on one side and MMS on the other side, it may not exist, even if both sides have identical preferences. So there are multiple impossibility results, and the question is, if this is indeed the case, then what do we do in terms of the recommendation fairness problem that we have in hand? So this is the overall structure. Again, to recall that we are trying to have EF1 among all the customers and alpha MMS among all the producers. And what we for this, we use this pipeline where we take the data and use a recommendation algorithm, and it really does not, I mean, we can use any recommendation algorithm depending on what kind of data set we have. And then the idea is to use that relevance scores as valuation functions, and then using this tools from the space of allocation of indivisible goods under constraints, and also making sure that we are ensuring two-sided fairness guarantees. We provide an algorithm that solves this particular goal. So our proposed algorithm goes in two phases. In the first phase, we would copy each producer. We will make MMS copies of each producer, where MMSJ is a value that can be computed easily for each producer. This is the maximin value for each producer, assuming that the producer's valuations are just one whenever they are matched. And then we start with an arbitrary ordering of all the customers, and then allocate using a modified version of greedy round robin algorithm. So the modification is required to ensure that the feasibility constraints are all met. And also the EF1 for customers is being maintained at every iteration. So once we do that, we would end up getting an allocation which is envy-free, but it may not ensure that every customer has got exactly K recommendations. So there can be some slots in some of the customers' allocation which is like less than K. So then if that's true, then we go to the second phase. Then we reorder all the agents according to the topological ordering of the envy graph for the partial allocation that was obtained in the first phase. And using that, we allocate greedily in a round robin way while ensuring feasibility. So the question is, of course, we know that because of the impossibility result, we cannot really have EF1 and MMS simultaneously on two sides. But what we could achieve using this algorithm is that it returns EF1 allocation among all the customers, and it ensures non-zero exposure guarantee for all the producers. So each producer at least receives a value of 1. Further, it ensures alpha MMS guarantee to at least a large fraction of the producers. So this fraction you can read it as like if, let's say, if alpha is equal to close to 1, then this the second term is mostly like K by M, where K is the number of slots and M is the total number of producers, so which is a very small value. So 1 minus that fraction of at least 1 minus that fraction of producers would achieve their alpha MMS if we use that particular algorithm that I just showed. And then we show that this algorithm runs in polynomial time, so it's easily computable, and we can actually use it. Okay, so what we do is to compare our algorithm, we use a couple of data sets, and I'll show you the results for one of these data sets, which is Google local ratings data sets. And in this data, there are around 11,000 customers on one side and 855 businesses on the other side, and more than 25,000 ratings. So we compare our algorithm with top K recommendation algorithm that just takes like top K relevant producers and shows it to the customer. So note that this top K is going to have 0 envy. So this is an envy-free algorithm because every customer is happy if we do a top K. So this particular graph on the left side shows, in y-axis, we show average envy, and this is 0 for top K. However, for our algorithm, this is very close to what top K is able to achieve. And another algorithm that we compare against is random, which picks a random K producers and shows it to the customer. And as we see that the envy using random K is a bit higher than top K. And next, on the right side, we measure customer side utility. So top K gives, so we use top K as the standard for utility, and then look at what fraction of other algorithms are able to reach but in terms of customer utility. So what we see is our algorithm is very close to what top K would do. And as we can understand that random will not really do a good job in terms of accumulating good utility for customers. So we see a lower value for random K. So those were consumer side results. Now, if we look at the producer side results, then in the y-axis here, we are capturing the fraction of producers who have achieved alpha MMS. So in this particular on the left side, what we see that if alpha is equal to 1, that is, if we are trying to achieve absolute MMS, then empirically our algorithm is actually always fair towards the producer. Whereas if we look at top K, it is just fair on 20% of the producers. And then random is fair on around 50% of the producers. And on the right side, we have changed like alpha values and increased it. So again, when alpha is equal to 0, any allocation is fair allocation because the threshold is 0. And when we increase alpha, we see that the fraction of producers who achieve that alpha MMS fairness kind of drops for top K, but it remains consistent for our algorithm. So overall takeaway here is that with less than 10% loss in customers' utility, our algorithm is able to achieve this two-sided fairness, at least empirically. At this point, I'll stop for a while and check if there's any questions. Okay, if not, so I'm not able to see the Q&A at the text section, so please unmute yourself and ask questions if you want. Okay, great. So next, I'm going to switch to like another paper. So if there's no more question, this is going to be a slightly different setup that I'm going to talk about. And so this is joint work with Shivika Narang and Narhari Aditi. And this paper is called On Achieving Fairness and Stability in Many-to-One Matchings. So the motivation of this work is to is college admissions in engineering colleges in India. And what we aim here is to find a fair as well as stable many-to-one matching. Now, the scenario is as follows, that we have a set of students who are ranked based on their scores in the All India entrance examination. And then there are engineering colleges which are also ranked based on their on-campus job offers that they provide, the faculties that they have recruited, and also reputation that improves over years. So we have some kind of a ranking among the college and ranking among students. And here we are trying to match N students to M colleges, basically matching a subset of students to each college in a way that every student is being matched to at least some college. Okay. Now we care about two main properties. So we want stability in the matching solution and also fairness. What do we mean by stability? It's the presence of no blocking pair. And this is standard in matching, where we say that a blocking pair is a pair of student and college, such that the utility of the college for this student is actually higher than the utility of the student who has been matched to this college currently. So if that's the case, and simultaneously, if there is at least one student in this college who has been matched to this college whose value is actually lower than this particular student we are talking about, then this causes a blocking pair, because they won't really want to go with the matching solution, because they are better off by stepping out of this of the matching solution and creating their own pair. So that would cause instability. So we just want stability in the matching by not having any blocking pairs. And second is we want fairness, because there are so the fairness arises mainly from the college side, where the low ranked colleges, the new colleges that are new engineering colleges in India, which have competitive quality, but they are kind of ranked low just because they are new. And then many seats in these colleges remains vacant. Now the question is, can we try to improve that without causing a lot of unfairness on the student side? So can we have some fair matching, which is fair across all the students as well as all the colleges? So for this particular problem, we would look at the fairness notion called Leximin optimality, where we would try to maximize the utility of the worst of agent, and then the second worst of agent, and so on. And the problem statement now is, can we find a Leximin optimal stable matching? So in the what we investigated is if there are global rankings, as I described, like if we know that for sure there is a ranking among all the students and there's a ranking among all the colleges, and then whatever utility values are put in, these values would adhere to those ranking. And if there are strict preferences allowed, then we have positive results. Because with strict preferences, we have a certain structure to this problem, in the sense that given any instance of a strict ranking, a matching is stable if and only if if and only if the matching is like this, that the first college is matched to some top K students and the second college is matched with the next bunch of K or like K2 students and so on. So if this structure is maintained, then this matching would be stable, and this is like an if and only if condition. So this structure is obtained with strict ranking. And then for Leximin optimality, we just need to figure out what is that good partitioning point so that the entire allocation remains Leximin optimal. So first we would look at an easy setup where we would assume symmetric utilities, that is the utility that a college gets after matching is same as the utility that the student gets. So there's like a utility given to the pair of matching. And with that assumption, we would provide an algorithm that actually gives a Leximin optimal stable matching. So the algorithm goes as follows, that we initialize with a student optimal stable matching. Now, by student optimality, we mean that it's Leximin optimal on the student side, and also it's stable. So how do we do that? Note that if we match the least ranked college with least ranked student and do a one-to-one matching until we reach the top college, and with top college we match whoever is remaining. If that's the scenario, then this is student optimal. And you might think that what happens if there are budget associated to each student. We also have it's a bit more complicated the way we do the initialization, but it's also possible. So we show that even with budgeted setting, this entire a version of this algorithm would work. So for now, we will assume that there is no capacity constraint. And then this is the student stable matching. Now, once we have this kind of a matching, then at every turn, we would try to increase the number of students in the lower ranked colleges, just to make sure that the Leximin tuple is higher and higher. So what we want is to kind of maximize the worst case agent and then do the same with the second worst case and so on. So the question is how many students we should put down would depend on a fact that it should not hurt other colleges, in the sense other colleges should not get lower utility than the last college. So there needs to be a look ahead, and we propose like how do we really compute this look ahead in a tractable time. And we need to keep doing this for every college and repeat this step. So we show that this entire thing can be done, and it takes order of mn time to compute a Leximin stable optimal stable matching. And it's really the stability that gives this structure to this problem. And then we just need to look at like the partitioning points. So overall, these are the key results that we give in the paper. So one is if we assume symmetric valuation and strict ranking, then we have this order of mn time algorithm. However, if we do not assume symmetric valuation, still a version of this algorithm is able to give Leximin stable matching. It just requires more computation time. And we also show that if we go to weak preferences instead of strict preferences, then it's hard to get a Leximin optimal stable solution. And this can be shown by reduction from a balanced partition problem. And for ranked valuation, when we do not have symmetric assumption, with weak preferences, the problem actually becomes APX hard. So yeah, so this is the main results that we have. And this one can be obtained by reduction from a decision version of bin packing problem. Okay, and some of the other results that we have is that is there a one-to-one matching algorithm under general rankings for a constant number of colleges? So we have a positive results where we say that even if the rankings are general, in the sense we don't even need to have a global ranking, then if there are 2 colleges and n students, there is a way to find out the Leximin optimal matching, which is actually also MMS on the college side. The next result that we also show that is it possible to obtain EF1 fairness along with stability in many-to-one matching, and we show a counter example with 2 colleges and 4 students showing that this is not really possible. And we have multiple other impossibility results in the paper. So in summary, we have explored the space of two-sided fairness and looked at very restricted some problems in this space, and we have positive results for scenarios where there is a many-to-one matching with rank preferences and symmetric valuations, or even without symmetric valuations but rank valuations. And then we have somewhat we have EF1 plus MMS guarantee for a large section of population on the other side in situations where we have this many-to-one kind of a matching with a lot of cardinality constraints. So this is a summary of all the results that I discussed today. And yeah, I mean, I aim to continue working towards providing decision support solutions to socially impactful problems, and I'm hopeful that we together will be able to successfully grow this space of research. And with this, I would pause now and see if there are more questions.